GenAI and MLOps Part 13. This episode has 13 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Vertex AI Feature Store. How would you design feature freshness, offline or online consistency, access control, lineage, and monitoring for a feature store on GCP? Here's a strong way to approach it. Define ownership and SLAs for each feature, including freshness, allowed lag, and backfill behavior. Keep offline training features and online serving features generated from the same transformation logic where possible. Track lineage back to source tables and pipeline runs. Enforce access with IAM and data governance policies. And monitor missing values, distribution changes, stale features, and training serving skew. Nice. Let's continue. Question 2. Vertex AI Model Monitoring. What would you monitor for skew, drift, attribution drift, data quality, prediction quality, and alert fatigue? Here's a strong way to approach it. Monitor input schema validity, missing or null rates, feature distribution drift against the training baseline, training serving skew, prediction distribution shifts, and business or label-based quality metrics when ground truth arrives. Tune thresholds with minimum sample sizes and persistence windows. Route only actionable alerts to on-call, and use dashboards or tickets for lower severity drift so monitoring improves reliability without creating noisy pages. Great. Moving on. Question 3. Vertex AI CI or CD. How would you build a CI or CD pipeline that packages training code, compiles pipelines, runs evaluation gates, registers models, and promotes deployments? Here's a strong way to approach it. Use CI to lint or test training and pipeline code, build and scan containers, push images to artifact registry, and compile the Vertex AI pipeline spec. The CD path runs the pipeline in a controlled environment, evaluates metrics against thresholds, registers only passing models, and promotes to staging or production through approvals or automated canary checks, with rollback handled by redeploying the previous registry version. Alright, next question. Question 4. Vertex AI Security. How would you secure Vertex AI workloads using least privilege IAM, service accounts, VPCSE, private networking, CMEK, and audit logs? Here's a strong way to approach it. Give each pipeline, training job, and endpoint a dedicated least privilege service account rather than broad project roles, and avoid long-lived keys. Use private networking where supported. Restrict data access with VPC service controls for sensitive projects. Use CMEK when encryption key ownership is required. Keep artifact registry and data stores locked down, and rely on cloud audit logs plus labels to trace who trained, registered, and deployed each model. Let's keep going. Question 5. Vertex AI Cost Optimization. A Vertex AI project has rising training and prediction costs. How would you analyze spend and reduce waste without hurting model quality? Here's a strong way to approach it. Start with billing export by project, label, model, endpoint, training job, region, and skew to identify whether spend is coming from training, online prediction, batch jobs, GPUs, idle replicas, or logging. Reduce waste by right-sizing machines, setting endpoint min replicas appropriately, scheduling non-prod shutdowns, using batch prediction for offline workloads, caching or batching requests, pruning unused models or endpoints, and comparing cheaper model sizes against quality metrics before changing production. On to the next one. Question 6. MLflow reproducibility. What exactly would you log in MLflow so another engineer can reproduce a model months later? Here's a strong way to approach it. Log the code version, dataset snapshot or query or version, feature transformation version, parameters, metrics, random seed, library or environment file, training container image, model artifact, evaluation report, and any pre-processing artifacts. The goal is that someone can reconstruct not just the trained model file but the exact training context that produced it, which is essential for debugging, audit, retraining, and rollback. Good. Here's another one. Question 7. MLflow Artifact Storage. How would you design MLflow tracking server, backend store, artifact store, access control, backup, and retention in production? Here's a strong way to approach it. Run the MLflow tracking server stateless. Store metadata in a managed database such as Cloud SQL or Postgres, and store artifacts in durable object storage such as GCS or S3 rather than local disk. Protect it with SSO or gateway off. Restrict bucket or database access with least privilege. Back up the backend store. Define retention for old runs or artifacts. And monitor server latency, database health, storage growth, and failed artifact uploads. Nice. Let's continue. Question 8. MLflow CI or CD integration. How would you integrate MLflow with GitHub Actions, Jenkins, or Cloud Build for automated training, evaluation, registration, and deployment? Here's a strong way to approach it. Have CI test the training code and build the training or serving image. Then run training in a controlled job that logs metrics and artifacts to MLflow with the Git SHA attached. A promotion step compares metrics against thresholds, registers a model version only if it passes, and triggers deployment to staging or production through an approval or canary gate, with rollback pointing the serving layer back to the previous registry version. Great. Moving on. Question 9. MLflow versus Vertex AI. When would you choose MLflow, Vertex AI experiments or model registry, or use both together in a GCP MLOps platform? Here's a strong way to approach it. Choose MLflow when you want open source portability, framework neutral tracking, and a registry that can work across clouds or self-hosted Kubernetes. Choose Vertex AI native tracking and registry when the platform is strongly GCP managed and you want tight integration with Vertex AI pipelines, endpoints, monitoring, IAM, and audit logs. Many teams use both MLflow for experiment tracking and collaboration, then publish approved models into Vertex AI for managed deployment and monitoring. Alright, next question. Question 10. MLflow model serving. How would you deploy an MLflow model for real-time inference using Docker, Fast API, Kubernetes, Kserve, or a managed endpoint? Here's a strong way to approach it. Package the MLflow model with its dependencies and signature, then choose a serving path based on control needs. MLflow's built-in serving for simple tests, a Docker or Fast API wrapper for custom pre-processing and APIs, Kserve or Seldon on Kubernetes for production traffic management, or a managed endpoint for lower operations overhead. Validate input schema, add health checks, observability, canary rollout, and a rollback path to the previous registry version. Let's keep going. Question 11. MLflow governance. How would you enforce model ownership, approval gates, lineage, security scanning, and compliance evidence using MLflow metadata? Here's a strong way to approach it. Use required tags and registry metadata for owner, data source, git commit, pipeline run, risk tier, approval status, and deployment target. Then enforce promotion through automation rather than manual UI changes. Store evaluation reports, bias or explainability checks, vulnerability scan evidence, and approval comments as artifacts or registry notes so the model's path from experiment to production is traceable for audit and incident review. On to the next one. Question 12. Kubeflow components. How would you package pipeline components as containers, pass artifacts or parameters between steps, and keep them reusable across teams? Here's a strong way to approach it. Package each component as a small container with a clear command, pinned dependencies, and explicit input or output contracts. Pass lightweight values as parameters and larger files or models or reports as artifacts in shared storage. Version component images in artifact registry. Document expected schemas. And avoid embedding project-specific paths so the same component can be reused across teams and environments. Good. Here's another one. Question 13. Kubeflow distributed training. How would you run distributed TensorFlow or PyTorch training on Kubeflow with GPUs, node pools, retries, and checkpointing? Here's a strong way to approach it. Use Kubeflow training operators such as tfjob or PyTorch job. Schedule workers on GPU node pools with node selectors, taints or tolerations, and resource requests, and store checkpoints in durable storage so failed jobs can resume. Monitor GPU utilization, logs, and job status. Set sensible restart policies and back-off limits, and validate that distributed networking, image dependencies, and data access work before scaling to expensive multi-GPU runs. Nice. Let's continue. That wraps up this episode. Nice work practicing, and see you in the next one.